So now that we totally understand pressure, let's start looking at the gas laws. And our first gas law is going to be Boyle's law. And there's Robert Boyle down there. Really cool looking guy, I suppose, right? Now, remember back in the day, assuming you had a consistent amount of gas, and sooner or later we're going to have to deal with what that means. Hint, it involves moles. But assuming you just have a set amount of gas in some container, you could then make it expand and contract. So, and there's three variables they were mostly concerned with then. Eventually, like I said, we got to throw moles in that. But back in the day, there were three variables they were concerned with: volume, pressure, and temperature. So you have a set volume of gas, you change the pressure, what happens to the volume? You change the temperature, what happens to the volume? Maybe change the temperature, what happens to the pressure, whatever. So you play around with those three variables, and the gas can expand, contract, do whatever. Figuring out the details of how exactly that worked, what they had to do was use scientific method. Only change one thing. Only look at one thing changing. So we have a bunch of different gas laws because everyone chose a different thing. Boyle decided he wanted to see what pressure does to volume of a gas. So notice we have an independent and a dependent variable. If I change the pressure, what happens to the volume? Okay, and that's what Boyle focused on, and so that's what his law is going to be about. Tomorrow we'll look at some French guy who came along and said, oh yeah, well, what if I change the temperature and then hold everything else constant? What happens to the volume? But we'll stick with Boyle, a good English guy. So again, you have to hold everything constant. Constant amount of gas, constant temperature. You can't let the temperature change. Because if you do, that might have affected the volume of gas. You don't know. So hold everything constant and only change the pressure. And then what happens to the volume? Now, you guys already know this. If you take a gas in a cylinder and you push down on a piston, you'll compress the gas and make it smaller. So if you increase pressure, the volume decreases. A mathematical way of saying that is pressure and volume are inversely proportional. They vary opposite each other. And how you show that, of course, you have to hold temperature and the amount of gas constant. Obviously, if gas is leaking out, the volume is going to change. Obviously, if you're heating or cooling, the volume is going to change. You want to take those out of consideration and keep them all constant, only change the pressure. And then it's a nice direct proportion, or nice inverse proportion, I should say. If I double the pressure, the volume goes down to 1/2. If I triple the pressure, the volume goes down to 1/3. 10 times the pressure, the volume is 1/10. So it's an outright mathematical relationship there, very clear cut. Boyle gets his name on this law not because he realized that gases shrink when you press on them. Everyone knew that. He gets his name on this law because he figured out the absolute mathematical relationship. That is in an inverse proportion, just like you saw in algebra or whatever. The way it looks mathematically is volume is proportional to, this little symbol is Greek letter alpha. It means is proportional to rather than is equal to. Volume is proportional to the inverse of pressure because it's inversely proportional. Mathematically, the inverse is the reciprocal. So volume is proportional to 1 over pressure. Now, these proportions, they're not equal to each other, but they vary in the same way. So how you get rid of the proportion symbol and make it an equal sign is you add in a constant of proportionality. And so it's going to look like that. V equals K times 1 over P. Or simpler, V equals K over P. I wrote it this way so you can clearly see that we put the constant of proportionality in. Notice again, chemists use K for constant because we don't know how to spell. Now, so this still shows it's an inverse relationship, but now we have a constant. The actual value of that constant isn't terribly important to us because the value of the constant will change if you change the temperature, or if you change the amount of gas. So that constant depends on these other factors I'm not messing with. It's only constant because I'm not messing with them. But again, it wouldn't matter what the constant was other than I might need it to calculate one thing or the other. So we're going to find a way to get rid of the constant. How we do that is we notice if I multiply both sides by p, You can play around on a piece of paper if you want to show the algebra works. Multiply both sides by P, the pressure here cancels, and you get PV equals K. Or another way to say that is pressure times volume equals a constant. Again, so you can clearly see as pressure goes up, volume's got to go down to equal that same constant. All right? Now, we get rid of the constant by using changing conditions. So I'm going to go up to my whiteboard and show you that. But we're going to get P1 V1 equals P2 V2. And here's how that happens. Now, imagine I have a container holding a gas. Now, that's a cylinder, and this is a piston on top of it. Now, it should be actually hitting the walls because it's got to be airtight, obviously, right? By the way, a piston is nothing more than essentially an airtight movable lid. So I got a rod up here that I can push down on if I wanted to. So right now I'm pushing down on this with some pressure, let's call it P1. It's pressure condition number 1. And the volume inside here is V1, volume condition number 1. And of course we know P1 V1 equals some constant. Whatever that constant is, who cares? Now, let's take the same exact gas in the same exact container, but now I'm going to push down harder up here. So now I'm going to try to draw it looking exactly the same. It's not, but I'm pushing down harder, which means the piston gets pushed down further. So now I'm pushing with a new pressure, larger pressure, P2. See how I made the pressure look larger by making the arrow bigger. And the new volume in here is V2, which clearly you can see is a smaller volume. Now, what if I multiply these pressure and volume together? P2 times V2 equals, now, sometimes I get people wanting to say, well, it must equal K2. But no, it's not a new constant. That's the point of Boyle's law. No matter what you do to the pressure, the volume changes so that it equals the same constant. Okay? So P2 times V2, it's the same gas, it's the same temperature. They must equal the same constant as P1 times V1 equaled. Okay? So P1 times V1 equals a constant for that gas under those conditions. P2 times V2, new pressure, new volume, equals the exact same constant as long as I don't change the conditions. So, if you remember from way back in Algebra 1, maybe I guess it was, there's some property, I forgot what it is, maybe reflexive property, something like that. If A equals C and B equals C, then A must equal B. Okay? If P1 V1 equals a constant and P2 V2 equals the same constant, then here we get what we were looking for. P1 V1 must equal P2 V2. And that's the form of Boyle's law we usually use, because you'll notice now it got rid of the stupid constant, which we don't know what it is anyway. So yeah, that's Boyle's law. Pressure 1 times volume 1 equals pressure 2 times volume 2. Notice that means I'm going to have to give you conditions. Say I have a gas stored at 10 atmospheres at 30 liters of volume. Change the pressure to 7 atmospheres. What's the new volume? Well, clearly you can just plug the numbers in and do some simple rearranging and get the answer, right? This is simple algebra 1 at this point. And by the way, you'll notice it works very similar to what we had with molarities and volumes. M1V1 equals M2V2. Remember, we did that with titration with the acid and the base. The equation works the exact same way. I give you the initial conditions, pressure and volume. I give you one of the final conditions, the new pressure or the new volume, and you find the other one. It's really that simple. And by the way, while I'm here on my whiteboard, I should show you a quick graph of what this looks like. If we put pressure on the x-axis, because that's our independent variables, the thing we're changing, and volume on the y-axis, the graph is going to look like this. Okay? That's what an inverse proportion looks like. If you were to graph y equals 1 over x, that's the graph you'd get. So notice down here at very low pressures, the volume is very large. But as the pressure gets bigger, the volume shrinks as Boyle predicted. Notice at zero pressure, the volume would expand to infinity. Well, but that's just vacuum of space now. And at infinitely large pressure, way over here off the chart, the volume would collapse down to zero. Well, we can't get to infinite pressure, but the closer you get, the more compressed your gas gets. Now, in reality, of course, sooner or later, the gas is going to deviate from this ideal behavior. It's going to leave the graph because eventually the molecules are going to be forced so close together, those intermolecular forces we talked about are going to make them stick and form a liquid. So maybe right here, in reality, the gas would become a liquid, then the volume just drops way off. And it stops following the gas laws because clearly it stops being a gas. Okay? So we're going to work with what we call ideal gases. Gases that follow these gas laws perfectly. Real-world gases will eventually deviate from ideal behavior. And assuming we get time at the end of all this, we'll look at how and why more specifically. But before my time runs out here, let me come back to the PowerPoint. And let's look at a quick sample problem. If I give you 175 milliliters of methane, now, it doesn't matter that it's methane, any gas is going to follow the same law. That's the beauty of the gas laws. It applies to every gas, no matter what it is, until we deviate from the ideal. But again, that's something we'll look at. We're going to always assume gases are ideal for our calculations. So we got 175 milliliters. That's the volume. Call it V1. And it's stored at 125 kilopascals of pressure. That's pressure P1. So now I'm asking you what new pressure, what P2, is needed to make the volume 50 milliliters, V2. Now, what about units? Do I have to convert these? Luckily, since this is a proportion, no you don't. As long as your units are consistent. I used milliliters for volume here, I have to use milliliters for volume there. As long as it's the same unit, I don't have to convert anything. If I gave you milliliters here and liters down there, then yes, you'd have to convert one so that they're equivalent. But it wouldn't matter which one you use. Same with pressure. I used kilopascals here. That's fine. Your answer is going to be kilopascals. If I had given you atmospheres, no big deal. Your answer would have been in atmospheres. So use any units you like as long as you're consistent with Boyle's law. Other gas laws may vary. So there's the equation. Now, we know P1 is 125, V1 is 175. So plug them in. Equals, we're looking for P2, what pressure, and V2 is the new volume, 50 milliliters. Plug it all in. Now multiply these, divide by 50. You guys know how to do algebra 1. We get a P2, if I did my calculating right, of 438 kilopascals. And that's it. If you want another sample to try, there you go. Here, notice I give you pressures in torrs. No big deal. You can plug it in with torrs. I give you volumes in milliliters. Again, no big deal. Just plug it in with milliliters. Plug into the same equation, and you're done. All right, I'll give you a worksheet to do on this for tonight, and that will do it for today's lesson. Tomorrow we do a new gas law.